Okay, ji, Bismillahirrahmanirrahim. Welcome to another lecture of modern control systems. I'm your presenter Mohammad Rafe Chukhtai. The topic of today's lecture is basically state variable models, and we will also see a few signal flow graphs in this lecture as well. So first of all, what is a state variable model? Earlier in previous lectures, you calculated the transfer function of a system in S domain. You first of all modeled a system mathematically with the help of Newton's laws, and after modeling the system, you were able to write differential equations of the systems. And after writing the differential equations, you can convert those equations into S domain, and eventually you were able to fetch out or write an equation in terms of output over input in S domains, which we called earlier as a transfer function. Now we can also find the transfer function of a system without going to the Laplace domain. We can find the transfer function of a system in another way using state variable model. So just like I explained in previous lectures that these are all the different techniques which simplifies our calculations, or uh, every technique has some benefit over another. State variable model has few benefits of its own. Similarly, signal flow graph have their benefits. Similarly, block diagram have its benefit. Laplace have its benefit. Every technique used in the control system makes your life easy, makes your life simple, helps you basically. The core reason of these techniques is to help you analyze the system, is to help you evaluate the stability of the system, or is to help you to learn the system. Eventually, you can design a better system by using these techniques. And obviously, learning these techniques individually is one thing, but moving from one set to another is another thing that we should know and we should study in order to look into the systems in details. So state variable model is just like Laplace model. Mathematical modeling is another way to represent any control system. It has its own benefits, it has its own usages. We will discuss those in this lecture, but you should be convinced that like signal flow graphs, like block diagram reduction, like other mathematical models, like transfer function in S domain. You have a transfer function. Basically, transfer function in S domain is a way to represent a system. Similarly, state variable model, just like transfer function, is a technique to represent a system. Although we can go from state variable model to transfer function and transfer function to state variable model, but we keep these two as separate techniques or as separate models to visualize any system. And obviously, both of these models have their own benefits and offer their own insights into the system. We basically in state variables we make first order differential equations, and then we group the equations and make a matrix and solve for those variables. So without going into the S domain, it is more of a kind of matrices are involved in state variable models. And then once we find state variables, we are able to calculate the transfer functions directly from state variables using, there is a formula that we will discuss later in time, which uses the state variables to find the transfer function of a system. So we can go directly from state variables to transfer function without going into the Laplace domain. And it is especially helpful to find the transfer function of time varying system. To find the transfer function of time varying system by conventional methods obviously is somewhat difficult, but finding the transfer function of time varying system with the help of state variable models makes life easy. So this is what up till now we have discussed, that what is the state variable, why the state variable model exists, and how it is different from the others. Now, what actually is the state variable model? There are two words, state variable and state variable model. There is one is state and one is complete state variable. What is a state of a system, and what is a state variable which defines the state of a system, how we define these two things, and what is a complete state variable model. This we will discuss shortly. So first of all, I would like to explain what is actually a state of a system. What is a state of a system? Basically, state of a system is a set of variables such that knowledge of these variables and input will provide the future state or output. Obviously, if we are given with the equations that provides the dynamic, that is, if we are given with, uh, for example, let me give you an example. If we have a mass spring system, if we have a mass spring system and we know that this is mass m and it is being pulled downward, uh, we know the initial position of mass, initial position of this mass, and secondly we know the speed or velocity with which this mass is moving. So these two variables define the state of a system. We can say that we have a mass m and which is currently at position this and moving with velocity this. This defines, these two variables are enough to define the state of this system. That is, this system is currently in this state. It has this position and it has this velocity. Now, if someone wants to find a final position after some time, final position after 2 minutes or after 3 minutes, then he only needs the initial position before. What was the position before 2 minutes, and with what velocity it was moving. So by these two information, he would be able to calculate his answer or the final position of the system. So these two variables or these two uh, 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 states of a system are enough to find the final position of a system or the final state of the system. So state or state variable, state is basically a set of state variables, uh, knowledge of those state variables and the equation describing the dynamics. Obviously, if you know position and velocity, you want to know the final position, you should know this formula as well. So this is understood that you should know the equation that providing the dynamics of any system which is under discussion. So if you know the equations and if you know the state of the state variables or the state of initial state of the system, then you are able to calculate the final position or future state or the output of the system. These basically state variables describe the future response of the system given the present response, excitation inputs, and equation describing the dynamics. So we can say in this system, position and velocity are can we can say that position and velocity are said to be the state variables. For example, if we say that taking it into the mathematical form, if I say what I am actually saying, that x1 of t is my one state variable and x2 of t is my another state variable. I'm saying that there are two state variables of this system. One is x1 of t and one is x2 of t. x1 of t is the position, which I am saying y of t, and x2 of t you can say velocity, or which is dy of t over dt. These are the two state variables of this system. Now, if you know the differential equation of the mass spring system that we discussed earlier was m d square y over dt square plus b dy over dt plus ky is equal to u of t. Uh, that was the differential equation that we discussed earlier for this mass spring system. When we write this equation in terms of our state variables, which we have defined over here, we can write it as m dx2 over dt plus bx2 plus kx1 is equal to u of t. Or I can alternatively, if I rearrange it, I can write it as dx2 over dt dx2 over dt is equal to minus b over mx2 minus k over m x1 plus 1 over m u. And another equation we have dx1 over dt is equal to x2. dx1 over dt is equal to x2. How? x1 is y of t, and dx1 over dt is equal to dy over dt, which is actually x2. So we have these two equations. One is the differential equation of state variable x2, and another is the differential equation for state variable x1, and both are single order first order differential equations. So this set is actually set to be a state variable model. We can alternatively write it as x1 dot is equal to x2, or rather I would like to write it as just for the understanding, so that it is easy for you to understand things in future. I can write it as x1 dot is equal to 0 x1 plus 1 x2 plus 0 u. Similarly, x2 dot is equal to uh, minus k over m x1 minus b over m x2 plus 1 over m into u. Now if I try to write it in matrix form, I can write it as x1 dot x2 dot is equal to 0, 1 minus k over m minus b over m x1 x2 plus 0, 1 over m into u. This basically defines the first part of your state variable model. Second part is related to output. We will discuss it shortly as well. But for right now, for the timing, you can say that this set of equation defines your state variable model. What was our starting point while defining a state variable model? we are given with a system, and first step was to choose state variables. In this system, in the given system, we chose position and velocity as state variable because by these two variables we have enough information that we can find the output. Now, the important point to note is uh, the state variables may not remain same uh, for a given system. Let me write it as a bullet point. State variable mm, are not unique. Let me write it in this way. State variables for a given system are not unique. There is a person. If you give same system to two persons, one can set the state variables as position and velocity, and another person can have another state variables. He can say that acceleration or something, or starting point or acceleration, any other parameter which helps him to find the final output or the final state. uh, he can choose some other state variables. So state variables are not unique, but the important point is, state variables should be, how can I phrase it, state variables should be minimum set of variables. For example, in this system, by position and velocity, these two informations were enough for us to find the final state of the system. If I say that position, velocity, acceleration, and there is resistance and spring constant, I define all those as state variables. That I have a mass spring system with mass this, position this, velocity this, acceleration this, moving in east direction, moving in south direction. I can take all these as state variables, but they would be redundant. My answer can be found by these two state variables only. There can be another set of state variables. Those variables can also be in two in number. Maybe they can also give you the same answer. They can also give you the required information. They may not be position and velocity, but they might have the potential to tell you the output of the system. So you can choose those sets as state variables. So the first step is to choose a state variables which helps you to find the output goal. This point will be more clarified in next example that I am going to discuss. Uh, but for the time being, we started with any system. The first step is to find a set of variables which completely defines the current state of the system, and by using those set of variables along with the input and the equations describing the dynamics, you can easily find the output of the system. This is the concept of a state variable model. Now if I take another example of let's take LC circuit. This is a current source. Let me connect a capacitor over here and inductor over here, and this RLC circuit and resistor over here. Let me call this current as IL and this current as IC, and this is positive, negative. This is the voltage across capacitor VC. And this current, source current, is U of T. If you want to find the output resistance, the voltage across the output resistance or any parameter, any voltage across anything in the circuit or any current, if you know about, if you have an information about capacitor voltage and inductor current, can you find the output voltage? Yes, you can. Similarly, one can say that if I know inductor current as well as the resistance value, I can find the output voltage if this is the output voltage. Yes, you can. So I hope that with the help of this circuit, you might be able to visualize that there can be multiple sets of state variables which helps you to find the output of a system. So set of state variables is not unique, but it should be minimum possible set of variables. So by inductor current or value of the resistance, you can find the output voltage, or if you know the capacitor voltage and inductor current, you can also find the output voltage. So by using the KVL or loop analysis. However, there are obviously, the point is that there are multiple options from which you can choose to select your state variables. However, as a convention, normally we choose capacitor voltage and inductor current as state variables. It keeps our calculation simple, and these are, you can say, these are the most famous state variables whenever we have capacitor and inductor in a circuit. So capacitor voltage and inductor current are the most desirable options for your state variables. So I would also like to take capacitor voltage and inductor current as my state variables, and can obviously write any equation, or I can write my state equation with the help of these two state variables. So if I say that capacitor voltage is Vc is equal to x1, where my x1 is one state variable, and if I say IL is equal to x2. So x1 and x2 are my two state variables. Um, x1 is capacitor voltage and x2 is the inductor current. Now, if I try to write the equations of the system, I can, if I write IC, if I try to write the capacitor current equation, it is C dVc over dt by general circuit analysis knowledge is equal to U of UT, or U of D is the input current, minus IL minus inductor current. Or there is another equation that I can write, LdI over dt is equal to minus RIL plus Vc. And if I want to write the output equation, then output equation V naught is equal to RIL. So just by the previous knowledge, I have written these three equations of my given RLC circuit. Now I will now convert these three equations into my state equations. How? Um, dx1 over dt is equal to minus 1 over c x2 plus 1 over c u of t. Just visualize from where, pause this video and try to visualize from where I have written this equation. 1 over c u of t, 1 over c u of t, see this is, if you focus on this equation, dvc over dt, Vc is your capacitor voltage and capacitor voltage is your first state variable. So dVc over dt can be written as dx1 over dt. Similarly, u of t, this u of t is divided by this C, and this IL is inductor current, and inductor current is your second state variable, which is x2. So minus 1 over C, this C into x2. So this equation has been written in the form of in terms of these two state variables. What is our goal? Our goal is to have two equations, one in the form of dx1 over dt and another in the form of dx2 over dt. So let's see how we can write the equation in terms of dx2 over dt. I would recommend to pause this video and try to write the equation for dx2 over dt. So guys, dx2 over dt is equal to 1 over lx1 minus r over lx2. How? di over dt, di over dt, where I is the inductor current and inductor current is x2. So this di over dt will be converted into dx2 over dt. This L is divided on the right hand side of the equation. IL is x1, so 1 over L x sorry IL is x2, so minus R over L x2. VC, capacitor voltage, is x1, so 1 over L x1. So these two general circuit analysis equations have now been converted into state equations. And another for output equation, if we try to write this output equation in terms of state equation, we can write output V output is actually y of t is equal to R into x2. There is no x1 in output equation. So now we have three equations. This was the second part that I was talking about. This is also the part of your state variable model. So let me try to write this in the form of a matrix. X1 dot x2 dot is equal to 0 minus 1 over C, 1 over L minus R over L into x1 x2 plus 1 over C and 0 into u of t. So these two equations are written in the form of matrix over here. And another equation is y of t is equal to, you can say, 0 r to x1 x2. So these are the two equations. Now let's try to generalize this. Uh, we have discussed two examples. One was our conventional mass spring system and another is simple RLC circuit. And we tried to write the state variable model, state equations. First of all, we selected the state variables, then we wrote the state equations of the system, and then we defined that overall state variable model. Position and velocity over here define the state of the system. These two equations define the position, velocity are state variables. dx2 and dx1 over t, these two equations are actually state equations, and this complete is state variable model. So you must know the terms state variables, state equations, and state variable model. Similarly, state variables over here in this example are capacitor voltage and inductor current. These are the state variables, and These two are the state equations, and this box is the state variable model. So if I try to generalize this for n states, if we have a system with n states, then we have equations like this: x1 dot is equal to a11 x1, where a11 is some variable, or sorry, some constant multiplied with x1, plus a12 x2 plus a1n xn plus b11 u1 plus dash 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 b1m um. So you might have equations like this. Similarly, for x2 dot is equal to this, and x3 dot is equal to like this. So you have equation for, if you have n states, then you have xn dot is equal to this. So it would be kind of n cross n matrix over here. So the if we try to write it in terms of matrix, then it would be like x1 dot, x2 dot, and xn dot is equal to, this matrix would be n cross n, a11, a12, a1n, a21, a22, a2n, similarly an1, and this is ann, multiplied by x1, x2, and xn. I am trying to write the above thing in generalized form. Plus, similarly, the constants with the input b11, b1m, bn1, and bnm with u1 and um. So this matrix is called A matrix, this matrix is called B matrix. Similarly, let me choose another pen. This matrix is called C matrix, and if there is an input u, something multiplied with input, then that matrix would be called as D matrix. Over here there is nothing multiplied with the u, so input, so there is no D matrix over here. So overall we can say, we can define a state variable model as x dot is equal to, now I am writing it in terms of matrix, ax plus bu, and y is equal to cx plus du. So now whenever someone asks you to find a state variable model of a given system, he is actually asking you to tell him what are A, B, C, and D matrices. So A, B, C, and D matrices actually define your state variable model. You can find this here. The A matrix is, sorry, here the A matrix is this, B matrix is this. Here A matrix is this, B matrix is this, C matrix is this, and D matrix is a null matrix. Similarly, for any system, your first step is to find the state variables. Next, you have to write the equations for those state variables, which would be called as state equations. Once you have written the state equations, you can make a matrix out of these state equations, and you can tell the value of A, B, C, and D matrix, and this A, B, and C matrix will give you a state variable model. So I believe you are quite familiar now with what state variable model is, what are the states of the system, what are the state variables, and what are the state equations, and what are the state variable, and what is the state variable model. Now there is a very small derivation which in itself isn't that much important, but its result is actually important. So let's try to go through that derivation. I will try to skip few steps and write things directly so that I tell you exactly why that derivation is important. So up till now, we know that x dot is equal to ax plus bu and y equal to cx plus du. This is the state variable model. Let's try to find the solution of these two equations, vector solution of these two equations, to kind of look inside this state variable model. How can this state variable model be useful? So just to look inside into it, we will solve these two equations. State variable model, concept of state variable model finishes in on these equations. Now we are trying to uh, kind of look into it and see uh, how much further information we can extract from this state variable model. So if I try to apply Laplace on this equation, I can write it as s x of s is from Laplace, minus x of 0, okay, is equal to a x of s plus bu of s x of s minus a x of s is equal to x of 0, just by I am rearranging the system, and from here I can write x of s is equal to x of 0 divided by s minus a plus b into u of s divided by s minus a. Now by actually taking inverse Laplace, now if I take the inverse Laplace, I can and by using the partial fractions, I can write x of t is, I am directly writing this equation now, e raised to the power a t x of 0 plus integration 0 to t e raised to the power a t minus tau b u of tau d tau. In matrix form, I can write it as e raised to the power, in matrix I write it as x of t is equal to exponent a t x of 0 plus 0 to t integration exponent a t minus tau bu of tau d tau. Now if we take direct Laplace of this vector form, we can have x of s is equal to si minus a inverse into x of 0 plus si minus a inverse into b u of s, where this si minus a is actually the Laplace transform of exponent at. This holds importance. This you can say is called the state transition matrix or the fundamental matrix, which is being defined as denoted as phi of s. This Si minus A inverse is of very critical importance in control systems. That is why I didn't skip this derivation, and I wanted you people to know that from where this Si minus A inverse term came from. It is actually from the solution of your um state equations or state variable models. So this is state transition matrix or fundamental matrix, and it is denoted by phi of s. And in terms of this state transition matrix, we can write, taking inverse Laplace transform, we can write x of t is equal to phi of t x of 0 plus 0 to t phi of t minus tau b u of tau d tau. Uh, Now, one thing that you should note, that in this side of the equation, in this term of the equation, u of t isn't included, and in this term of the equation, there is no initial condition of the system. So we can say that this is this is basically zero state response. This overall x of t is the system response. This term indicates zero state response, and this term indicates zero input response. So by solving the state equation, we saw that we can find zero input response or zero state response. How we can find zero input response or zero state response? Zero input response is phi of t into x of 0. What is phi of t? Phi of t is exponent at. If you want to find it from your if you want to find it from your state variable model, this A is your state matrix A, and you just write Si minus A, take its inverse, take its inverse Laplace transform, you will uh, you will get exponent at, or you will get phi of t. When this phi of t is multiplied with x of 0, you will get zero input response. So with the help of your state variable model, you are able to find Si minus A inverse. A is your A matrix, A is your this matrix, A is your this matrix, A is your this matrix. So by using this A matrix, you can find Si minus A inverse. I is the identity matrix. So if your A is 4 by, let's say if your A is 2 by 2, matrix of 2 by 2, let's suppose if your A is, let's suppose 1, 2, 3, 4. Let's see, if your A is this, then Si minus A inverse would be S00S. This is Si minus this matrix 1, 2, 3, 4. Whatever the result is, its whole inverse. This will give you the fundamental matrix or state transition matrix. And with the help of this fundamental or state transition matrix, you can find the zero input response or zero state response of the system, and you can evaluate your system mathematically. You can evaluate your system for its properties. So that is why this is only an application of your state variable model. State variable model concept ended in this slide. In this slide, we just discussed the application of your state variable model. That is, we can find the zero input response and zero state response of your system with the help of state variable model. And how have we derived this? We actually have solved this equation and came to this conclusion. So this is basically your state variable model. Now there is one thing that I would like to discuss, that how to go from state variable model to a signal flow graph. Let's discuss this. Okay, in the remaining lecture, I will discuss two things. Number one, number one, I will calculate how to go from state variable model to signal flow graph, and second, how to go from a given transfer function to signal flow graph. And you already know that once you have signal flow graph, you can use Mason rule. If you have a signal flow graph, then you can find the Mason rule to find the transfer function. So you can go from state variable model to signal flow graph to transfer function, and similarly from transfer function to signal flow graph to state variable model as well. You should know about how to go at the moment you know this bit, how to move from signal flow graph to transfer function. You know that it is with the help of uh, your Mason's rule. Uh, Shortly we will discuss these two bits, this one and this one, from state variable model to signal flow graph and from transfer function to signal flow graph. So how can we move from state variable model to signal flow graph and from transfer function to signal flow graph? Okay, let's write a state equation for any system, or it would be great if I write the state equation for the RLC circuit that we have just discussed. In that system, x1 dot was is equal to minus 1 over c x2 plus 1 over c u of t, and your x2 dot was 1 over L x1 minus R over L x2, and your output was Rx2. This was the state variable model. Now, next thing is how can we model, or how can we make a signal flow graph with the help of this state variable model. First of all, to start with, uh, you always start with this equation. V naught is equal to Rx2. Let's say this is your output node and I denote it as V naught. This V naught is equal to R into X2. If I say this is X2 and this is multiplied by R, and in this direction it will give you V naught. Now I am trying to make a signal flow graph out of these three equations. A signal flow graph that satisfies these three equations. Now this is X2. Now I know that what is X2 or X1 dot. X1 and X1 dot is equal to basically dx1 over dt. Now if I want to go from x1 to x1 dot, it is simple integration. So if I want to go from x2 to x2 dot, if I want to go from x2 dot to x2, what should be written over here? You have dx2 over dt and you want to go to x2. So obviously if you integrate this x2 dot, you will get this x2. So what is the Laplace of integration? The Laplace of integration is 1 over s. So here I have written 1 over s. First of all, I wrote the output equation. Output equation was V naught is equal to Rx2. I wrote it in the form of signal flow graph, that is V naught is equal to R multiplied by x2. After that I converted that x2 into x2 dot. How? Because we already know that x2 dot is actually a differential of x2. So by taking integration of x2 dot I can get x2. Now what is x2 dot? From this equation x2 dot is 1 over L x1 minus R over L x2. That is, if I define another node and call it x1, then x2 dot is equal to 1 over L 1 over L x1 minus R over L x2 minus R over L x2. This node, just try to visualize or write the node equation for this node. Node equation for this node is x2 dot is equal to 1 over lx1 plus minus r over lx2, which is actually this. Now similarly, I write the equation of x1 dot. Here I will write 1 over s, and x1 dot is 1 over c u of t. U of t is your input. U of t is your input. 1 over c u of t minus 1 over c x2 minus 1 over c x2. So this graph satisfies all the equations of this state variable model. So now we have moved from state variable model to a signal flow graph. Now if I want to write a transfer function, or if I want to visualize any property that can only be seen with the help of signal flow graph, I can visualize it over here. Because this state variable model does not tell you how many loops are there system, is there any self loop, is there flana, is there anything. This state variable model gives you some limited information. Similarly, this signal flow graph gives you some another set of limited information. Now it's your choice, or it's depending upon your requirement. You can either stay in state variable model or you move to the signal flow graph. Now if I want to find the transfer function from signal flow graph, I will use a Mason's rule. So this loop has been completed. I can move from state variable model to signal flow graph to transfer function using this technique. So now I will try to write or draw a signal flow graph from transfer function. Let's discuss this bit now. Okay, in this slide we will try to move from transfer function to signal flow graph. How? Now let me try to write a transfer function of a system. A transfer function of a system. Transfer function of a system. Let me find some transfer function which I to start with so that I'm able to explain it to you people. Let's begin with this transfer function. We have y of s, which is output, over u of s, which is input, is equal to b naught divided by s4 plus a3 s cube plus a2 s square plus a1s plus a naught. This is I have written this transfer function from your book, from your Dorf book, so that it is easy for you to refer afterwards. So this is any of your transfer function, and you want to draw a signal flow graph out of this transfer function. Now what is the first step? The first step is to visualize this transfer function in the form of Mason's rule equation. Now what was the Mason's rule? To refresh, to just as a refresher, I hope it is with me over here. Yes, this was the Mason rule, and transfer function was of the form this. In the denominator, I had 1 minus loop 1, loop 2, loop 3, loop 4 plus 2 non-touching loops and this and that. Similarly, in the numerator, I had paths and their gains. In the numerator, I had paths and in the denominator I have 1 minus loops. How can I use this information over here to draw a signal flow graph from this transfer function? First of all, I will try to write this equation in the form of Mason's rule, which was in denominator I have 1 minus something. So dividing the denominator and numerator by S4, I have B naught S minus 4, and here I have 1 plus A3 S inverse. Dividing this with S minus dividing this with S raised to the power 4 gives you S inverse. Similarly, plus A2 S minus 2 plus A1 S minus 3 plus A naught S minus 4. Now, in terms of totally writing it in terms of Mason's rule, which was 1 minus, I have equation like this: B naught S raised to the power minus 4 divided by 1 minus sum of individual loops, which is actually minus A3S inverse minus A2S minus 2 minus A1S minus 3 minus A naught S minus 4. So my transfer function now look something like this. Now somehow I have a glimpse that I can now make a signal flow graph out of this transfer function by a kind of reverse engineering or anything. What was in the denominator? In the numerator? In the numerator we have paths. So how many terms are there in the numerator? In this transfer function, there is only one term in the numerator, which is b naught s minus 4. It means that we have a single path from input to output. As there is only one term, it means that we have only single path from input to output, and the gain of that path is b naught s minus 4. So let's try to make this gain of b naught 1 minus 4. If I have this node as an input node, which is u of s, and this is an output node, which is y of s, and there is a path which has gain b naught, then there is a node, then there is another path which has gain 1 over s, then there is some node, then there is a path which has gain 1 over s, and then there is a node, then there is a path which has gain 1 over s, then there is a node, then there is a path, and you reach u of s. Let me take 1 as its gain. So now what is the gain of this path from input to output? Gain of this path is b naught s minus 4. So this term has been addressed. Now let's talk about this term, minus a3 s inverse. Now I have multiple options to make signal flow graph. Uh, just to reiterate, transfer function is unique to a system. There is only one transfer function of a system. However, for a given transfer function, there can be number of ways to make a signal flow graph. There can be numerous uh, procedures to make the signal flow graph. If I write instead of writing b naught over here, I can write b naught over here and write 1 over here. Still gain would be b naught s minus 4. So obviously, however, the shape will change. So there can be more than one shapes of a signal flow graph of a given transfer function. Similarly, there can be more than one set of state variables for a given transfer function. So there can be more than one set of state variables. There can be more than one set of signal flow graphs given we have only single transfer function. So now to address this term minus a3 s inverse, I can either write a loop, make a loop over here and give it again minus a3, or I can make a loop over here as well. It makes no difference. However, the shape will change. The shape of the graph will change. Whatever the shape in either case will be, transfer function will be same for both. So this is minus a3 s inverse. This bit is addressed. To address this minus a2 s minus 2, I make a loop over here and call it minus a2. So this loop is minus a2 s inverse and s inverse, so minus a2 s minus 2. Similarly, this is minus a1 s minus 3, and similarly finally this is minus a naught s minus 4. So in this way I have made a signal flow graph with the help of by using a transfer function. As I said, there can be more than one type of signal flow graph for one system. So this typical type of graph is called phase variable canonical form. If you make a phase variable canonical form, why it is called phase variable canonical form? Because the node variable are phase variables x1, x2, x3, x4. Actually, I have oversimplified this graph for you people. It must have actually been drawn like something like this. Let me try to edit this graph, keeping its okay, it cannot be edited. Anyways, if I make a node over here, if I say that this is, I can say node x1. If I call this node as x1 and I make a separate node over here, then that node would be x1 dot. That node would be x1 dot, and if I say this is 1, there is no gain. It means I have splitted one node into two nodes. Just I have only splitted one node into two nodes to make you people visualize the phase variables. You can combine these nodes as well. You can say this is x1 dot, okay, no problem, but uh, for that you must have initial visualization. And similarly, if I say that this is x1 dot and this node is x2. So if these two nodes were a single node, then you might have been confused that I am writing that I am writing two names for one node. So that is why I have splitted these nodes into two. Why I am doing this, you will see shortly. Similarly, I make one node over here and call it as x2 dot, and I call this node as x3. Similarly, I make another node over here and this gain is 1. Similarly, I make another node over here and call it x3 dot, and this is called as x4. Sorry, x1 dot, x2 dot, and this x2 dot is x3. This is x3 dot, this is x4. Yes, this is x4, and this is x4 dot. So now if I try to write the equation of phase, why it is called phase variable canonical form? Because x1, x2, x3, x4 over here are phase variables. Or you can also say that these are state variables. Now how can I write the equation of the state variables? Let's try to write the equation for x1 dot, x1 dot is equal to x2 over here. That is what I am trying to say. Here x1 dot is equal to x2 because these are same nodes. You can see. Similarly, x2 dot is equal to x3 and x3 dot is equal to x4. Similarly, x4 dot, no, x4 dot will be different. X4 dot will be, x4 dot is minus a3 x4, or I let me try to write from the start. X4 dot is equal to minus a naught x1 minus a naught x1, and this node is also coming over here, which is x2. So minus a1 x2 minus a2 x3. So these are the state equations for your system, and the state matrix A over here would be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and minus a2 minus a1, sorry, minus a naught minus a1 minus a2 and minus a3. This is your A matrix. So this is your basically phase variable canonical form, and we have found the phase variables and we have made an A matrix. Just visualize that we started with a transfer function, we moved to the signal flow graph, and from signal flow graph we calculated your this state variables. So state variable model to signal flow graph, done. Signal flow graph to state variable model, done. This signal flow graph to state variable model, done. Signal flow graph to transfer function, yes, by Mason rule. Transfer function to signal flow graph reverse path, yes. This is transfer function to signal flow graph, yes, we can move from transfer function to signal flow graph. And signal flow graph to state variable model, yes, we have already discussed it. State variable model to signal flow graph, yes. So these all paths have been covered. Now let's try to take few more examples of your transfer function, few kind of complicated examples of your transfer function to signal flow graph. Let me take another example from your book. uh, Okay, I have this equation in front of me, which is basically y of s over u of s is equal to b3s cube plus b2s square plus b1s plus b naught divided by s4 plus a3s cube plus a2s square plus a1s plus a naught. Now this is my transfer function. What was the first step? First step was to uh, write it in the form of 1 minus and something. Write denominator in the form of 1 minus something. 1 minus sum of individual loop gains. So what I need to do? I need to divide numerator and denominator with this S4 to make it 1. So my transfer function would become 1 minus minus a3 s inverse minus a2 s minus 2 minus a1 s minus 3 minus a naught s minus 4, and my numerator will become b3 s inverse plus b2 s minus 2 plus b1 s minus 3 plus b naught s minus 4. Now let's try to make a signal flow graph from this equation. How many paths are there from input to output? There are four paths from input to output: b3 s inverse, b2 s inverse, b1 s minus 2, b1 s minus 3, and then there is b naught s minus 4. So what I need to do, first of all, let's eliminate this term b naught s minus 4. So what is b naught? For b naught s minus 4, okay, for b naught s minus 4, this is y of s, this is y of s, this is b naught. You can either write b naught on the right side or left side as you wish. B naught s minus 4, 1 over s, 1 over s, 1 over s, and then 1 over s. And let's say it 1 and then u of s. So from output to input, we have this one straight path, which is b naught s minus 4. So this term is addressed. Second term b1 s minus 3. Let's make an other path b1 s minus 3. So if I kind of take a point, pick off point over here and drop it over here, no. Let's erase this path. Okay, somehow it is not being erased. Let's use it for another term. The term we were discussing was b1 s minus 3. So s minus 1, till this node we have s minus 1, till this node we have s minus 2, and till this node s minus 3. Let's take a pick of point and drop it over here. And what is the constant b1? If I call it b1, then this path has gain of b1 s minus 3. Now it has b1 s b2 s minus 2. So I will take a pick of point over here and gain will be b2. Now there is another path starting from this node to this node to this node, 1 over s, to this node, 1 over s, 1 over s is minus 2, and then this b2. So this path has gain b2s minus 2. Similarly, there is a final path to the output, which is b3s inverse. So if this is b3, then this path starting from this node and then taking exit from here and landing direct at y of s, this path has gain b3s inverse. So we have addressed all our numerator terms. Now let's start to address our denominator terms. By the way, this can be different as well depending upon how you are taking the pick of point. We will discuss this shortly as well. Now let's try to address the your denominators. So first of all, it is, let's take this minus a3 s inverse, minus a3 s inverse. So I can call it minus a3. So this term is okay. Second term is minus a2 s minus 2. Loop is minus a2 s minus 2. So this is s minus 1, this is s minus 2. Take a pick of point over here, from here, and minus a2. So this complete loop has a gain of minus a2 s minus 2. So this term is also addressed. Next is minus a1 s minus 3. S minus 1, S minus 2, S minus 3, and take a point from here and call it and give it a gain of minus a1. So this loop has a gain of minus a1 s minus 3. So this gain term is also addressed, and last gain term is minus a0 s minus 4. So let's make a final loop from here to here and give it a gain of minus a4, sorry, minus a4, minus a0, sorry, minus a0 s minus 4. So this is the signal flow graph of uh, this equation. So we have finally made a signal flow graph. Its signal flow graph looks like this. Now what was the second step? Let's try to write uh, you can say the state variable model for this signal flow graph. Just like our last practice, if I say this is x1, then I make a node over here and call it x1 dot. This x1 dot when multiplied with 1 over s gives you x1, and I call it here, I um, say that there is a gain of 1 and call this node as x2. Similarly, making another, splitting this node into 2, calling this node as x2 dot and calling this node as x3, and this gain is 1. Similarly, this is x3 dot, when multiplied with 1 over s it will give you x3, and this gain is 1, and calling this node as x4. Similarly, this node is x4 dot. So now let's try to write the equation of this system. It would be simply it would be similar to the last equation. We have x1 dot is equal to x2, x2 dot is equal to x3, x3 dot is equal to x4, and x4 dot is equal to, no, x4 dot is equal to what? X4 dot is equal to minus a naught x1, minus a naught x1, and then minus a1 x2, minus a1 x2, and then minus a2 x3, and then minus a3 x4. So the A matrix, and obviously I'm not writing the output matrix, A, the other B, C, D matrix. You can obviously write those matrix by yourself as well, because output over here is y is equal to B naught x1. So if y is equal to B naught x1, so matrix C is, so anyways, let's write all the matrices. Matrix A over here is equal to 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, minus a naught, minus a1, minus a2, and minus a3. This is A matrix. And B matrix, there is no u in, oh sorry, I have missed this u of s. plus u of s. I missed this u of s in the last equation as well. Yes, over here. In x4 you have this u of s as well coming into it. So plus u of s. So when you write the B matrix, so your B matrix would be 0, 0, no x1, no x2, no x3, and for x4 you have, in x4 equation you have 1. So B matrix would be this. And your C matrix over here will be, there is no x1. Okay, there is one B naught x1, there is 0 x2, 0 x3, 0 x4, and D matrix would be null matrix over here, 0 0 matrix. So we started with this transfer function. We wrote it in the form of Mason's rule, and then we drew a signal flow graph out of it, and then we wrote the state equations or state variables A, B, C, state matrices A, B, C, D from this signal flow graph. Um Now let's try to write the same transfer function in some other form. Let's try to write the same transfer function in some other form. Mm, okay, let's check another possibility. Let me use this red marker. So let's again rule out all these options. Let me see if I can erase anything. Okay, it erases everything. Okay, anyways, first of all, let's address this term b naught s minus 4. To address this term, we will write, we will draw a path from input to output with again b naught s minus 4. Now, for this time, let's take b naught on the left hand side. We have output y of s, output node y of s, and we have input node u of s. From this input node, let's say we have again b naught, and then we have some node, and then we have 1 over s, we have another node, we have then again 1 over s, we have another node, again 1 over s, again another node, again 1 over s, again another node, and then this y of s. So now I have tried another option to make another different type of signal flow graph from this using the same transfer function. So this is b naught. This path has the gain b naught s minus 4. So our first term is has been addressed. Next path is b1 s minus 3. b1 s minus 3. b1 s minus 3. So if I move a pickoff point from here and drop it over here with again b1, then one path was this path. This is a second path to move towards the output, and its gain is b1 s minus 1 s minus 2 s minus 3. So b1 s minus 3, this term is also addressed. Now another term is b2 s minus 2. b2s minus 2. Pick another path over here and drop it over here. Let's say its gain is b2, and this path has the gain b2 s minus 1 s minus 2. So our another term is also addressed. Last term is b3s inverse. To address this path, take another pickoff point from here as a fourth path and drop it over here and call it b3, and this is b3s. This path has again b3s minus 1. So our all paths are addressed. Let's move towards the denominator, which gives you loops. So first is a naught. Let's first of all address a naught as minus 4. A naught as minus 4. Move a point over from here and drop it over here. So say that it has gain a naught. So this complete loop has gain a naught s minus 1, s minus 2, s minus 3, s minus 4. Now let's go to another loop. This term is addressed. Next is a1 s minus 3, sorry, minus a naught. Next is uh, minus a1 s minus 3. So for minus a1 s minus 3, it would be like s minus 1, s minus 2, s minus 3. Start from here and drop it over here on this node and take its gain minus a1. So this loop has minus a1 s minus 3. Similarly, minus a2 s minus 2 should be drawn like this. Minus a2 s minus 2, and similarly, okay, I am short of space. For last bit, this is my last loop. This loop is minus a2s minus 2 and minus a3s inverse. This is minus a3. This small loop is minus a3s inverse, and this is minus a2s minus 2. So you see, for same transfer function, this was the transfer function, and for this transfer function we have made two types of signal flow graph. This is the signal flow graph for the same transfer function for this transfer function, and this is also signal flow graph for the same transfer function. Now let's try to write the state equations quickly. Let's try to write the state equation of this system using the same approach. If I say that this node is x4 dot, if this node is x4 dot, then 1 over s is basically, if I say this is x4, this into 2, this would be x4, this would be x3 dot, this would be x3, this would be x2 dot, and then this would be x2, this would be x1 dot, and this would be x1. So writing the equation for x1 dot is equal to, what is x1 dot? X1 dot is this. So this x1 dot is basically minus a3x1 plus b3u of s. This is the x1 dot. It has two flows coming into it, uh, or rather three. One is minus a3x1, then b3u of s, then x2 plus x2. Similarly, x2 dot is equal to minus a2x1 plus b2u of s plus x3. Similarly, x3 dot is equal to, this is x3 dot, this is equal to minus a1 x1 plus b1 u of s plus x4, and x4 dot is equal to b naught u of s, simply b naught u of s. and you have y of s, y is equal to x1. Simple, y is equal to x1. So what are the matrices? Your A matrix is equal to minus A3, 1. You have minus A3 x1 term and x2 has 1 in it, no x3, no x4. Similarly, in x2 dot equation, you have minus A2 x1 and you have no x2, you have 1 x3 and no x4. And similarly, minus A1, 0, 0, 1. And finally, for x4 dot, you have 0, 0, 0, 0. No x1, no x2, no x3 and no x4. Sorry. X4 dot has b naught u of s plus this bit. This is minus a naught x1. This is minus a naught x1. So it would be minus a naught 0, 0, 0. This is your matrix A. And your matrix B would be equal to B3, B2, B1, B naught. Your matrix C is equal to 1, 0, 0, 0 because it has only x1 in it, and matrix D is again a null matrix. And this type of signal flow graph is called input feed forward canonical form, because you can see input is fed forward. Input feed forward canonical form. Last one was phase variable canonical form. This is input feed forward canonical form. Input is fed forward. Input is fed forward. You can see in all equations, you can see the input. In all equations, you have this input term. So this form of signal flow graph is called input feed forward canonical form. And these both are phase variable canonical forms. So now for the same transfer function, you may have different signal flow graphs and you may have different set of state variables or state matrices. For this transfer function, for a same transfer function, you have this state matrix A, this is B, this is C, this is D. So state variable model, this state variable model and this state variable model are different for a same transfer function. So the state variable models may be different, can be different. One system may have multiple state variable models, just like we discussed earlier. That to find the output voltage, you may select different information, different parameters to evaluate the output of a output voltage of a system. So similarly, we can have multiple sets of you can say state variables to find the output of a system. So by these examples we have witnessed that that for one same transfer function we have witnessed multiple signal flow graphs as well as multiple state variable models. So that's all for today. Again, if you have any questions related to this lecture, you can write me at rafe.choktai@uet.edu.pk. Okay, guys, thank you for your time. See you in next lecture, inshallah, and Allah Hafiz.